Swayam Prabha. Digital India. Educated India.
So then, and other thing I want to let you know is all of design and really real life also is an iterative approach. You will never be able to start at the beginning, go until the end and get an answer and turn the pages and say, yeah, I got the right answer. There's no such thing. You will always have to iterate answers. Okay, these are lessons we don't learn in 11th and 12th. We are used to very clearly stated problem statements and very clearly obtained answers to the third decimal point or whatever, and we don't realize that there is a lot of like uncertainty and iteration that we have to do. So, by the way, this presentation I give it to my undergraduate students in the third semester of engineering design. In the beginning, just to give them a perspective, I keep trying to reiterate this point, and it's very hard for people to change their mind. They're still used to that nice 37-degree inclined plane, right? So after doing JE for so many years, but I just try to tell them that it's. So then I'll talk a little bit about what is called configurational design and detailed design, and prototyping idea. We'll see. I won't have time, I think. So please let me know when I have to stop if there's a break or something sometime. 4 o'clock. Okay, good. Okay. So now we'll go forward and I'll explain what is engineering design. Yeah, questions? No. So what is engineering design? So first, basically a scientist is a person who creates explanation of how nature works. That is right now where you are all at. You are trying to understand how nature works, and honestly the end user for end customer for a scientist is literally themselves, and at the most a few of their peers, somebody who else is working in that area. So if I am satisfied with that answer and if they are satisfied with the answer, pretty much we are okay. It will be a very small select group of people. That's what scientist does. However, an engineer usually has to work on creating products, but we try to use this. We use these explanations. Okay, I am telling you, without doing any science, also engineers can create products. Literally, if I went to Velachery and asked one of the, there'll be cycle repair shop, there'll be somebody sitting there. If I ask them to do make a trebuchet, make something that will throw a object 2 meters away, they will sit down, tinker, they will put one a joint here, they will put one spring there, and they'll make it work. Okay, so that is fine, but they are still not engineers yet, they are tinkerers, because an engineer uses the science, engineering science, and so that you can start going towards optimization. Okay, but that said, the point that I still said is true. To be perfectly honest, do you all know when the first steam engine was done by, who was it? Who made the first steam engine? Not James Watt. Okay, thank you. Somebody else. Anyway, it doesn't matter. Some X created it. But do you know when they did it? Around which year? Late 1700s, let us say 1750, 60, 70, around that time. But actually, that is all the steam engine description. The science that went behind it is the science of thermodynamics. Do you know when that was created? 1850 or so, or literally 100 years after the steam engine was running. The first law of thermodynamics, second law of thermodynamics, which are all the basic stuff we learn right now before we study a steam engine, was all created 100 years afterwards, right? So in other words, a tinkerer actually built it without knowing any of the science. Okay, and it's possible, and I tell you, I would say literally a large fraction of devices or discoveries are still not too science based. You get it from your intuition, you look at how things work and you will see maybe this will work, and then you will put the science around it and present it in a nice clean package as if you thought of it all very scientifically. It's not like that at all. So, but anyway, but point is but that said, we still use the science very carefully we use the science in order to try to come up with better products. So when you if you ask some little kid, what do you want to be when you grow up? Supposing they say they're going to be a doctor, then if you ask them why, there's money. I know I've not met a little kid who's so mercenary. Usually, what else they will say? Save lives. I want to serve society. I want to serve people is what they'll say. But supposing you happen to come up across somebody who says, I want to be an engineer when they're growing up. If you ask them why, save machines. Huh? No, actually, so that's right. They will say something like that. They never will say, I want to serve society. But actually, they are also in the business. They are also in the business of serving society. They are in the business of saving lives. You won't believe the number of devices doctors are using right now to, right, all by engineers, right? So, but we unfortunately don't view it like that, and unfortunately that lack of doing that way prevents people from coming up with better designs. If I know that, hey, I'm doing this to serve society, you will immediately I'm guaranteeing you will come up with a better design than otherwise. Okay? Please do stop me if you're having any questions at all. So, they develop products, engineers develop products and processes which will allow the people to identify this thing, and so you have to satisfy the need. So you have to identify the need of the customer. You can't do everything for everybody. You have to clearly know, okay, this person wants a cheap phone. It's not going to do like a very high resolution images. It will not capture, but it will be cheap. So if that is a need, I will deliver that. On the other hand, the person has tons of money, and I can give you however high fund camera is there. I will do so. So I have to know the customer need. So, and then this is the most important. Yeah, I'll just, okay, go ahead, ask the question. Yeah. No, please go ahead. Yeah.
So sir, you were talking about engineering, sir, like how engineering can be used as a service. So I was thinking, as the human body already mentioned is not like an effective machine in itself. We have cancer, Alzheimer's, diabetes also, sir. And now there are numerous machines, like for those who have lost arms or legs, paraplegic, they have created arms and legs which can actually feel, things just like how a normal arm and leg can. So, sir, are there any ways we can use that to innovate in things like diabetes, sir? Because diabetes is caused by deficiency of insulin and excess of blood sugar. So maybe we can create a system that filters out blood sugar and injects more insulin, sir.
Certainly. So that is definitely one of in fact in our department we have a Center of Excellence for Diabetes Research, and certainly, as she pointed out, people are trying to develop prosthetics to try to improve people who don't have the use of their arms and legs, all the way up to trying to fix any imbalances in the body, which lead to, for example, things like diabetes or blood pressure, right, and so on. So in this process, we have to identify. So, for example, talking about just diabetes as an engineering delight, okay, it is actually one of the most complex control systems. As she pointed out, the body senses the amount of sugar and appropriately produces insulin to make sure you are maintaining the levels to within limits. Now, this is nothing but what is called a control system. We have a control system in this room to measure the temperature and switch on the AC if the temperature becomes too warm. Okay. So, unfortunately, the control systems that we have in this sort of engineering systems are very simplistic. You just switch, if the temperature comes down, you will switch on the AC, you will switch it off. Unfortunately, in the body, the problem is there are multiplicity of things going on. It depends a little bit about how your gut is digesting the food, at what time scale, the food is getting digested. Okay, how effective is the extraction of the nutrients from that? All of that affect your overall like insulin, presence in your body, sugar presence, and therefore insulin. So in other words, what you're saying is absolutely right. I'm not denying what you're saying, just telling you that it's a much more complex control systems problem, and we are definitely, like, people are looking at it from that point of view.
What innovations also happen, sir?
What
Innovations have also been brought about, sir?
innovations? Very good. So what innovations, for example, in like this, say, a study of diabetes? First, we have to first write down a mathematical model of what's going on. To be perfectly honest, there are not so many very recent papers. In fact, yes, yesterday one student in our department presented a paper about a mathematical model of it. So where they literally write dm by dt, where m is the mass of food you eaten. So dm by dt, starting from there, how much various mechanisms will go all the way to the amount of blood sugar. So and then you problem with these sort of models, and they're good. You will have some coefficients for, you'll have alpha dm by dt. It will not, and you won't know what that alpha is. So you can only calculate that alpha by continuous glucose monitoring. So this particular paper, which is about a year old, where they did a continuous glucose monitoring, they just put this armband and see, and as they're eating food, you have to take the photograph of the food and how much exercise you are doing. So you have to first build a model. You have to first build an understanding of what is going on. That is that model is nothing but an engineering model. Literally a differential equation. It's the same thing, similar kind of model that people have built about how a internal combustion engine is converting fuel gas air mixture into useful work. Similarly, only thing is that is much simpler compared to this. Okay, good. Any other questions? Yeah.
From the definition, identifying problem, developing a solution, satisfying the need in front of country. What's the difference between an engineer and an entrepreneur then?
Entrepreneur, yeah.
Those entrepreneurs essentially do the same thing.
Yeah.
Business.
Yeah. So very good question. So what does an entrepreneur do which is different from an engineer? Nothing. So an engineer can be an entrepreneur. If you don't do an engineering entrepreneurship, if I identified that this friend of mine needs a pizza at 12 o'clock, let me come up with a system to deliver the pizza. I'm still an entrepreneur. I may not be an engineer. So the engineering thing is where we are working with products and processes which have to do with our broad engineering background, which takes in science and so on. But by that said, if you do this well, strictly speaking, if you identified the social need really well, and if you satisfy the need in a proper fashion, from there to a step to become an entrepreneur is like completely trivial. Whereas a guy like me, who is sort of somewhere between an engineer and a scientist, I'm also interested in fundamental understanding of how the material behavior is happening. I may not convert it into something that a society needs right away. There's still a part of me that is being satisfied. So in other words, what we are saying is, in an academic environment like an university, a person like me, I'll be doing some of this stuff, but I'll not look at the need directly from literally a customer endpoint. I'll not know whether one customer requires it or 100 customers require it. Right? All of that I will not look at. But from our department, there have been so many students who have gone and become entrepreneurs from engineering design department. Like, Aether, the students from our department. Yes. Like literally their first two Dabbas bikes are right now as they worked on it, and they are final year project. Then there are not only that, there's one more company coming up who do image guided neurosurgery. They've made the product for 8 years. They worked hard on it. They built a product. Now big companies like Medtronic are trying to buy that and all that. So there are such companies, and there are so many others. There's Shira, Medtech. There are so many guys who started companies out of it. So as long as you absorb this principles and then use your engineering principles well, you will be able to come up with something that will satisfy the need of the. Okay. So. Yes.
One more question.
Certainly.
Let's just, is it fine if I rename the word need to being a problem statement kind of a statement, say?
Convert satisfy the problem statement instead of saying satisfy the need.
And let's take the example like you just said, the necessity to understand what exactly the need is the most crucial part in trying to solve any problem.
Very good.
And this is the problem of medical technology start only when you do not know which exact point. You cannot pinpoint the problem because there are way too many parameters which are being taken into consideration. And as an extension, does that fall into the domain of a scientist who has not completely understood every parameter and how it functions?
Okay.
So, how do you address this problem when it starts from the scientist, when the engineer has to only use the data which the scientist is given by the definitions?
Okay. So, very good. So, I'll just rephrase his question to make sure that I understood it and that everybody understood it. So, the point is, like, if you take this, particularly the topic of a medical engineer, somebody who's going to make a medical device for the human body, for a doctor. Okay. One of the problems you've said is that it's too complex. There are too many variables, too much stuff going on, and you don't know what is the need statement. Identifying the need statement is very difficult, is what you're saying. And therefore, what you are saying is that maybe a scientist can go to a little bit more fundamental understanding of the various facets, and therefore they may be able to come up with, provide some inputs to the engineer to come up with a solution. Is that the correct? Okay. So that is why you are right, and there is nothing to say what you said is wrong. We are constantly guided, and constantly we get inputs from the scientists. That's why I said there also, create the product using these explanations. Okay. But that said, the engineer somehow cannot afford to go to that rigor of science and the details of explanation of the scientists. Unfortunately, we do not have the time and the ability also, because not the ability, because it's just so the scientists will always make things in a much more clear cut problem statement, but real life there'll be lots of other crap. For example, if I gave you a problem, if I told you I'm going to take a ball and throw it, okay, and if I tell you what will be the range, if I ask you the question, all of you will be able to immediately tell me using the projectile motion formula. So that is what, like, generally the scientists will do. They have neglected air resistance. Okay, but in real life there will be air resistance, and that air resistance will become so complex. If that also the physicists have worked on coming up with fluid flow problems. But literally, if I want to sit down and solve those problems of fluid flow around the ball as it is going, it will become a pain in the neck. I'll never be able to get an answer in like couple of years. However, I want to throw the ball right now. That's what society wants. Society doesn't want 10 years later. They want it right now. They want to have some answer right now. So what an engineer does is, they create rules of thumb. You will start simplifying your complex thing, but you will have to leave out stuff. Okay. So just to give you a very simple idea, so basically what we try to do is we really we make things simple, and we'll say, okay, you know what, because of this we'll lose some 10%, 20% accuracy. That's okay. We'll still get a ballpark answer. So similarly, coming back to the question that he asked, so strictly speaking, if you want to address as an medical engineer, you want to come up with a new device for a human being, strictly you have to go to the scientists, the biological scientists, and whoever does the genes and all that stuff, to literally get all the information, look at all the how the pancreas is working in terms of its chemical reactions, everything. You have to look at it, and you have to finally come up with an answer of what is the blood sugar level. But you don't have that. You don't have the time and like all the detailed information anyway. So as an engineer, what we will do is we will construct a solution which is a little bit more artificially stated, right, at a higher level, but we will try to, as I told you, we will still get some information, the dm by dt of how much the mass is being digested, how much mass of food, we will try to bring in some information, but at some places we will use some fudge factors. It will not be as clean a problem solution as like how a scientist would do it. So the engineer will have to start letting go of the, what do you call it, like, you know, yeah, it's you have to let go of some of the rigorous analysis you have to let go. Okay. So I think it's 3 o'clock. You want to take a quick break and we'll come back? Continue? For some more time at least, then okay. Is it okay, ma'am? Okay, we'll continue. So the idea, the key element of this entire process is we want to combine science, whatever science you learned. So honestly, in my subject that I am teaching right now, third semester, fourth semester, and even later my colleagues fifth semester, we'll still be going back to whatever science you've learned. I do still say F is equal to MA, and we solve problems using that. Okay. And in fact, literally, robotic arm, kinematics is a subject in our third years, like saying. That robotic arm is, you're using T is equal to I alpha, tau is equal to I alpha. Still we are using that. So we have to use that. I still have to do some integration if my heat transfer is happening in some weird fashion. Just today I wrote an equation, integral some q dot is a function of x. So it became an integral which you would have done in 11th and 12th. You would have done a lot of practice. We still have to do that. Okay. But at the end of the day, just now as that question that you raised, we have to combine with some experience to let go of some aspects and to take into some aspects. So if I want to throw my projectile and hit somewhere and I want to do an analysis of it, I'll have to get a feel for how much air drag is really important. If it's not so important, then I'll just work with that. Only if it's really important will I spend more time. So that is where we are talking about experience. Okay, and we have to make what are called rational decisions. We have to be very systematic about it. Okay, so but you have to keep in mind, and this is a point I'd like to make, that what is rational, what does it mean to be rational in your thought process? We all talk about it and we say it's important to do so, right? What do you mean by that? Without any? Without favoring anything. Without favoring, without being prejudiced or without being saying, yeah. Pure logic, no emotion. Pure logic, no emotion. He's also agreeing with that. Feasible, huh? Rational will be practical? Would it be?
It's not based on your intuition. It's based on logic.
It's not based on intuition, it's based on logic and facts, data.
Being the most optimized you can be.
Being as optimal,
yes.
Optimized.
For example, you have multiple different decisions you have to take. My emotional decision would be go play football. The most optimized decision would be go study rotational mechanics because I haven't studied it.
Okay.
So that would be a rational decision.
Okay. Okay. Being more optimal in your where you're going. Yeah.
Sir, in that when you've written key element there. Under key element. Combine science, math, and experience. Here is experience like empirical observation, or is it like stuff that you have designed before?
Very good. Very good. So the question here is, when I say combine with experience, I'm talking about some empirical observations. But again, see, and then I'll add to the question that I just asked. It's not different. So we just now talked about data and logic. Okay. But the fact is, first of all, the logic that we use is usually binary logic. If it's something or it's not something, that's all. 1 or 0. But actually, really speaking, most stuff is not binary. So we can say, this lubricant in this engine is not working. It does not mean it's not 0. It doesn't mean it's 1 or it's working means it's not 0 or 1. It's somewhere, it's like, where have I crossed the line is something that is not known. So it is not that easy, even though I say logic, that is not very clear. Second thing is data. You said we have to use the facts. You said you have to use the facts and so on, right? But which facts? Where do you stop? So right now, if I want to make a decision, as you said, regarding playing football, very excellent example, regarding studying rotational mechanics or playing football. Okay. So here, if I want to optimize it, and people have used the word optimizing also, I have to know that if I played football, maybe I will be more invigorated, maybe I'll do my rotational mechanics better, I don't know, or I'll be more tired and I may not study anything at all, I don't know. So in other words, all the facts are not available with me also. All data is generally not available with me. So even though I wrote here rational decisions, I personally am not a big votary or big supporter of so-called rationality. Like leaving out intuition, actually we are all guided a lot by intuition. Okay, yeah, go ahead.
Sir, the data you said, does it come from experience?
Does data come from experience? As it is written here, it is data, what we talk about.
Because taking the same example, if I had already done something like that before, I was already in that dilemma a long time before, I would know that if I go play football, I cannot come back and study, and I will take the better decision. So the data of previous experiences will help you when taking a decision in the future.
Excellent, excellent. So, so he's asking about like data. If you have, for example, data previously that you have played football and you were too tired to do, that will clearly make your decision better, and the data seems to be relevant data. Okay, is what he's saying. Well, to our experience, we do use such relevant data, but I don't know. Just because 5 times it happened that I was tired, today I might be in a mood where I actually go play and come, it will be better. We don't know. That's what happens. So lots of times we feel like we have, from our experience, we become prejudiced. Actually, this is what you're saying is a form of prejudice. You're saying, look, I have enough experience. In fact, that's what happens. If you go to a company, the senior most engineer will say, I know everything about this. They will never allow any change. Okay, and they'll say, no man, I have experience, man, this doesn't work, man, he'll say. But the current situation is we have better tools, we have better manufacturing technique, we have a different material. They're not willing to explore. Okay, so in a sense, have they become rational or they're irrational? Irrational only. So in other words, that's why I'm not very big supporter, even though I put the slide. By the way, I have to acknowledge one of my good friends, one Professor Arun Srinivasa from Texas A&M, who originally gave this talk, and we kind of worked with like these ideas. He worked with implanting them with me. So I have to acknowledge him. Okay. So when we always have discussions about this, and I was like, hey, come on, this doesn't make sense. But on the other hand, it's good to know that we have to do this process. Just because it's this is all irrational, I'm just going to do whatever I want, it doesn't fly. So as humans, we try to not work the extremes. We try to work with the middle path. Good, good. So, so therefore, a systematic process for this entire thing is necessary. I will leave this. I'll go a little bit fast. So basically, if you think about all the knowledge you acquire, okay. If you think at the very bottom is recalling information. 2 3s are 6. As a third standard kid, you would have, that is recalling. After that, you understand. Oh, I have 3 bags and 2 chocolates in each. I have 6 chocolates. You have understood it. That means you have interpreted, summarizing. Then you are also applying it. So now, if I know that there are 120 chocolates, I need 40 bags so that I have 3 chocolates per bag. You are applying it. You can apply knowledge. Okay. Then after it comes analysis. Okay. So you try to analyze the relationship. You will know that multiplication is nothing but a different kind of addition, and so on. So you can see just the same knowledge. It is got into different levels. Then finally, you have, these are the top 2 things. Literally speaking, this is where tomorrow you will all add value when you go on. Either you become a professor, or you are going to run your own company, or you're going to work in some job. Evaluating and creating, that is the skill that is unique to our. So all this bottom stuff but you need all this. You need to have recall information. You need to have that understanding. You need to be able to apply it in a few places. You need to be able to analyze it. But finally, if you do all of this, you'll be able to evaluate. So even evaluation is not that easy thing. You have to evaluate if something is not working. What is evaluation? If something is not working, where do you think it has gone wrong? and then creating is to come up something that will work. Okay, so this is the, I'm just going very fast through this. It's very, very famous Bloom's taxonomy, it's called, of how our knowledge is organized. Is it clear to everybody? I went a little fast. So this, so our design is always here, and that is the top of the knowledge pyramid. Okay, but by the same token, lots of people say, you know, why I don't need to remember anymore. Now everything is there in the phone. Okay, everything is accessible easily. I am not a votary of that. I feel like even now, even rote memorization is still good. I do believe that. Okay, because when it's in your mind only, you can take it and you can really organize, synthesize. Yes, only then you can really organize and synthesize, and you can come up there. If I know that there is some information about how an IC engine is made in some book, and I know how batteries, electric motors and batteries are there, it will not be enough for me to synthesize them and come up with a hybrid vehicle. Okay, I need to know the details of where that IC engine is internal combustion engine of a regular petrol car, where it will do what, and similarly I need to know what are the benefits and drawbacks of a motor, and then only I will be able to synthesize this too. So if you all get convinced somehow that anyway now you have to 11th and 12th, you have no choice, you have to memorize all your formulas. But if you think I'm only learning it for 11th and 12th and I can forget it, please don't. I want you to really take that into as a serious thing, that you want to keep these and they have to stay with you for a long period. There's a very, very famous Sanskrit Subhashitam which I love. Okay, it says, Pustakastha tu ya vidya parahastagatam dhanam karyakale samutpanne na sa vidya na tadhanam. So what it says, the knowledge that is there in the book, Pustakastha tu ya vidya parahastagatam, somebody else's hand is money. When the time comes, both are useless, because you cannot use that knowledge in the book, you cannot use that money of that person. Like Elon Musk has $300 billion. Does it help me buy one more car? No. That's this money, I am here, right? So Parahastagatam, like that, I don't want the knowledge to be remaining in the book. You should be putting it in your head so that you start integrating it. Okay? And this is some slightly tangential advice, but I think it's worth giving it to you. I've noticed how I've learned stuff over the years. When I was younger, when I was not getting chased by dinosaurs, I used to take books only and read, right? So that time, because the book could not be there with me all the time, I would have to kind of memorize it, and I would the way I took that knowledge and I constructed my own theory about it was very different from now how I'm doing it with my cell phone. So it's literally happening to me. I'll read some article in the cell phone. I say, oh wow, this is really interesting. And I'll put it away and I'll go to my colleague. We both will be playing tennis in the evening. And I'll tell him, hey, I read this very interesting thing. I'll start explaining it and I'll totally have a blanked out. Okay? I know it's interesting. I know he will find it interesting. But I have not synthesized it enough. Because I know, then immediately both of us will pull out, we'll start doing keyword search and we'll find it and we'll start explaining. But that is not good enough. That's not good enough. That's not how it used to be. When I was younger, we didn't have so many facts. Definitely now I have more facts at my fingertips. Okay, but whatever facts I had nicely synthesized them. If I had to tell somebody something, I was able to nicely organize my thoughts and come up with a nice, interesting way of presenting them. But now it's gone. So unfortunately, you guys all have access to information at your fingertips, and I'm thinking this has real consequences and problems. Okay, so please keep what I'm saying in mind. If possible, put your phone away and try to see if you can memorize stuff so that you remember with more detailed information. So right now, what other thing we do is I'll remember stuff at a more higher level. I'll say, hey, I don't need to know the Young's modulus of steel. I can always look it up. Okay? No, actually it matters. Even that matters. Going into all the detail and remembering it does help how your overall synthesis will be.
So why does Young's modulus of steel matter?
Very good question. I just gave the answer right, example right out of my top of my head, but it does, I am now going to like argue my stand. It does matter because of something that I teach in my class, but I have not talked about it. So, all the knowledge of engineering that we learn, okay, I try to put it into 3 categories. Okay, first category, what I call is literacy. Okay, so whatever we learn, I put in 3 categories. The first category is what I call literacy. The second category is what I call numeracy, and the third category is a word I made up called engineeracy. Okay, so when you talk about literacy, so supposing as an engineer you learned how to, let us say, design a bearing in a car or design a bearing. Okay, now that bearing could be there in a small artificial heart, or it could be there in a huge mining truck. They are also bearing, they are bearing. As an engineer, what you learn, you will not know both how to do this and how to do that. Okay, but you will know enough that tomorrow if you go to that particular company of that LVAD, left ventricle assist device of a heart, and if you know that they have a bearing and what are their requirements, you will have enough to read their relevant literature, either reports, and understand what they are doing. If you are done, for example, some other subject, if you are done like say English literature as an undergrad and come and read those reports, you will not be able to understand if same thing as, so you have now gotten literacy, not literacy as got defined by the government as, you know, reading your name and signing your thing. No, here I am talking about reading relevant literature and knowing its importance in, like, to a large extent. You may still have to read, you may have to go back to your textbook on design of mission elements and look it up, but at least you know enough. It's not, you're not starting from scratch. That is what literacy is. Numeracy is the second thing, talent, which I say you all have to keep in mind. By the way, this is all very broad. It is useful even for you right now. Numeracy is a feel for numbers. Okay, that numeracy you should always have. You should know, like for example, some basic, like what is the population of Chennai, stuff like that. And you should be able to estimate stuff. Numerically, you have to be able to estimate stuff. How many kilograms of potatoes do you think the residents of Chennai will consume in a day? Something like that. No, so then you have to be able to estimate it. You have to be able to estimate it, and you have to come up not only with a number, but with a range of error for your number. This is what I call numeracy. It's a very important and useful skill. It's very simple also. As soon as you open your newspaper and look at the front page, get a feel for what do you think will be the number of words in that page, or number of times letter S or letter M is appearing that page. Get an estimate. How do you get an estimate? And then check whether what will be the error range of your estimate. This is what I call numeracy. Okay, and the third is engineeracy, is a feel for engineering numbers. So what will be the diameter of a wire which will support the weight of my car? Okay, so yeah, literally I'm utterly jobless guy. So I go home, I decide I don't want to park my car in the garage, I want to hang it from the ceiling. Just like I hang my t-shirt from the hanger, I say no, I want to hang my car from the ceiling. So what should be the diameter of the wire? That is where some Young's modulus, strength and all of that will matter. So, okay, so what will happen is, for me to know relative magnitudes of various materials and what they can do, some engineering quantities are worth learning, is what I try to tell my students. Okay, because I'll tell you, you can always look up. You're right, no question. That answer is there for every knowledge that is out there. But what I say is, by that I don't want you to list out the table of Young's moduli for all the materials. I'm not saying that at all. But you have to get a feel for. I want, when I teach my heat transfer course, I'll say you should know what is the thermal conductivity of wood, coefficient of thermal conductivity of aluminium. Like few things you should know, so that you have a engineering feel for what will happen. Okay, you should know what will be the and other aspect of engineering field. One is this sort of numerical estimate. Second is conceptual estimate. You should know if you're sitting on the chair, the leg of the chair, is it, if it fails, is it going to fail in compression? Is it going to fail in so-called buckling? Is it going to fail in shear? So these are again the other engineering aspects that I tell my students that they have to learn. Okay. So in this, for that I made a long answer to a short question. But for this reason, I do believe that you have to, as you're going along, pick up some of these things, and it doesn't cost you. Your brain is big enough to support all of that. It's not as if you're burning an extra calorie of energy just because you learned you memorized the Young's modulus of steel. Correct? So please do that, and you have to similarly formulas also. Go ahead and learn, try to memorize the formulas, but by the same token you have to know its limits and all that. So it's okay. You have to learn and try to memorize as much as possible, and then learn how to derive it also, so that you will know its range of applicability. Okay, good. I know I went off a little bit on a tangent, but I think it's a very relevant tangent. At least it is something close to my heart.
Swayam Prabha, Digital India, Educated India.